Hello and welcome to example sheet 3, question 6. We're basically looking at a turbojet aircraft. I've took the images from the notes of the TS cycle and also the diagram of a turbojet engine here. I'm going to briefly run through that. You can find some more information and background reading on this on page 520 of the textbook, and there's also another example on page 522 of the textbook which I recommend you do. Just looking at this diagram now, so we're looking process 1 to 2. You can see from the TS diagram is isentropic, and that's the diffuser. So constant entropy through the diffuser. Process 2 to 3 is in fact compression, which is also isentropic. Now process 3 to 4, combustion. This is constant pressure heat addition. Process 4 to 5, isentropic expansion in the turbine. And finally process 5 to 6 is the nozzle, and this is isentropic as well. You can gather that information from the TS diagram. Now the questions ask for constant specific heats, so we're aware that we should be using the equations to solve this question. As always, give it a go with the tables as well. Okay, so there's a range of values given in the question. Velocity of 320 meters, altitude 9,150 meters. The ambient conditions, so this is the pressure at 1, which is 32 kPa, and the temperature at 1 is given as minus 32 degrees C, which of course we need to convert into Kelvin, which will give you 241 K. The pressure ratio across the compressor is given as 12. The temperature at the inlet of the turbine, so this is T4, is at 1400 Kelvin. The mass flow rate is given as 60 kilograms per second, and the calorific value of the fuel is given as 42,700 kilojoules per kg. There's a couple of things to know when dealing with jet propulsion cycle. The turbine work output is equal to the compressor work, because in fact we're actually looking at creating maximum velocity difference in order to maximize the thrust produced. Of course, you'll find the equation on the data sheet: force is equal to mass flow rate, bracket velocity exit minus velocity inlet. And finally, it's important to note that the kinetic energy is not negligible at the diffuser inlet and the nozzle exit. Finally, assume that the aircraft is stationary and air is moving towards it at a velocity of 320 meters per second. Ideally, air will leave the diffuser at negligible velocity. V2 is equal to 0. So we need to understand how to apply this steady flow equation to the diffuser. Okay, so E in minus E out is typically equal to the change in energy in the system. Since this is a steady flow system, we know that the energy change within the system is equal to 0, and therefore E in is equal to E out. So there's no heat or work transfer and no change in potential energy. Okay, so where of course this term represents the kinetic energy. So of course this term is represented by the enthalpy, so H1 plus V1 squared over 2 is equal to H2 plus V2 squared over 2. Here this is equal to 0 since the kinetic energy is equal to 0 at the diffuser, and therefore as a result the velocity at 2 is equal to 0. Watch out for the units here. When you mix velocity with enthalpy, enthalpy needs to be in joules per kg, not kilojoules. So okay, and rearranging this, subbing in the values, you'll find, of course, that times 10 to the 3 is to take into account that we need to be using joules and not kilojoules, and that'll give you a value of T2 equal to 291.9 Kelvin. Okay, so now we're interested in finding the pressure at 2. So T2 over T1 is equal to P2 over P1 n minus 1 over n to the power of that. Rearranging this, which is equal, and P2 is equal to 62.6 kPa. Of course, we know that process 3 to 4, the pressure is constant, so we know that P3 is equal to P4. So as you can see, we're working our way along calculating the values, and what we're ultimately looking for is the velocity at 6. This is what we're looking for, and we'll find the values along, and that's how we're going to calculate it. Okay, so looking at the compressor, of course we just said P3 is equal to P4, and P4 is equal to the pressure times ratio times P2, which is equal to 751.2 kilopascals. So this is a value for P3 and P4. Of course, we can use the equation given in the datasheet. T3 over T2 is equal to P3 over P2, K minus 1 over K. And you can rearrange this to find T3 is equal to T2 bracket P3 over P2, K minus 1 over K, and subbing in those values will give you an answer of 593.7 for T3. Now looking at the turbine, we know that as we previously stated, the work into the compressor is going to be equal to the work out from the turbine, which, since this is the jet propulsion cycle, so we know that H3 minus H2 is equal to H4 minus H5. Of course, when you look back at the diagram, you can see that quite clearly. Of course, since we're making use of the equation, Cp can be substituted with the temperature, and of course the Tp is cancelled, Cp cancels it on both sides, and T5 is equal to T4 minus T3 plus T2, and subbing in these values you'll find T5 is equal to 1098.2 Kelvin. Okay, so remember that process 4 to 6 is isentropic, so T6 is equal to T4 bracket P6 over P4 to the power of K minus 1 over K. Remember P3 is equal to P4, and we previously calculated P3, so we can quite easily sub in these values, and that will give you a value of T6 equal to 568.2 Kelvin. Apply the energy equation to the nozzle, and you'll see that H5 plus V5 squared over 2 is equal to H6 plus V6 squared over 2. and of course the velocity is negligible at 0.5. So rearranging this equation, h5 minus h6 is equal to v6 squared over 2, and Cp bracket t5 minus t6 is equal to v6 squared over 2, and finally v6 is equal to square root of 2Cp bracket t5 minus t6. And then when you sub all of those values in, you'll find v6 is equal to, don't forget 10 to the 3, we should be working in joules. And you'll get a final answer of 1032 meters per second velocity at exit. Okay, so part B of the question asks for the propulsive power developed. Okay, so from the data sheet you can find the equation for propulsive power. Wp is equal to mass flow rate bracket velocity at exit, which we just calculated, minus the velocity at inlet, and times the velocity of the aircraft. Now of course this part here represents the momentum equation. You'll get a value of Wp equal to 3670 times 10 to the 3 watts, which is equal to 13670 kilowatts, of course. Okay, scrolling up, part B, the rate of fuel consumption. Remember that this calorific value was given there, so we're going to use that. Mass flow rate is equal to Q in over CV, and Q in is equal to the mass flow rate H4 minus H3, and of course we can sub in Cp since we're using the equations, and subbing in the values. You'll find that Q in is equal to 48620 kilojoules per second, and of course now we found this value, we can find the rate of fuel consumption, which is, apologies, I should have made this clear, this is the mass of fuel coming in. So now we found Q in, we know CV because it was given in the question, so then quite straightforward, mass flow of fuel is equal to 48620 kilojoules second divided by 42700 kilojoules per kg. Of course kilojoules and kilojoules cancel, and the units balance, and the mass of fuel is equal to 1.14 kilograms per second. Thanks.